So this is the book that I'm following through right now. So some code which is there for I think chapter 5 is what I'm going through. So this is their official packet site, and this is where they have their code repo. And within this code repo, I'm looking at chapter 5. Chapter 5, first one is it? Yeah, yeah. So this is what I'm looking at, and I just gone and copied this code. I just the raw and just copied everything. I got it here. So let me cite the yeah. Okay. So and there is then this one, right? The first one, which is the official tutorial for beginners, the transfer learning tutorial. And then there's a second part to this also. The second part I've not gone through yet. The first part quite interesting. Uh, yeah. Then just wanted to understand how transform normalize is working because they've used it here, and I've seen this. Rather, I've noticed this for the first time. I've seen this earlier also in a couple of examples. So just to go through the transform. So what exactly is the transforms? So you compose this, right? So you compose this, and then so I tried playing around with this couple of times earlier also. Very interesting. So you can resize, you can center the image and things to center crop and everything. So over here, what is happening is resize is happening to 224 uh, pixels size, if I am not wrong, because the original images are from Cipher, and Cipher images are supposed to be smaller. And then you have this random horizontal flip, vertical flip, two tensor. So basically, the images will be transformed into a tensor. Then normalization will happen on three different channels, and this is the mean and this is the standard deviation. Now to understand this further, I need to obviously spend some time on this. And so here is a question that popped up, the first thing that popped up on the Google search. uh, yeah, so which one is that? No, this is different. This is the official tutorial. One second, I think I closed that. Very interesting question and lots of answers over there actually. So let's have a look. Yeah. So, and this answer is very, this is the most informative answer I already upvoted. Yeah. Why won't, yeah, but I think I've already upvoted, so it won't. Okay, so you and, okay, I already done. So normalize does the following for each channel. Uh, it is taking the image, so image minus mean divided by the standard deviation. The parameters mean standard deviation are passed as 0.5, 0.5 in your case. This will normalize the image in the range -1 to 1. Then people want to know how to normalize between 0 and 1 and 0 and +1 and things to that effect. So all that is explained, and then there is one I think over here. Yeah, transform.normalize, how to understand this. And of course, they have explained within their official tutorial also. So let me first quickly go through this official tutorial and what I really liked over it. It's written by Shashank Chilamkurthi. Okay, it's a wonderful tutorial actually, and he's referring to this another one, which is, if I'm not wrong, Stanford. Yeah, transfer learning, extremely again wonderful tutorial. It helps you understand whether what is fixed feature extractor versus what is fine tuning a convolution network. So I'll just quickly walk through this. So in practice, very few people train on an entire convolution network from scratch with random initialization, because it is relatively rare to have a dataset of sufficient size. So you will probably not be able to gather so many training images to have a sufficient size dataset, and that's why you might not want to train it from scratch. And because you will not be able to train it from scratch, you probably will go and pick up something like ImageNet, and from there, uh, you know, get features and get whatever else you can, so that you can use it for your own use case. Yeah. So that is what it. So instead, it is common to pre-train a convolution network on a very large dataset, example ImageNet, which contains 1.2 million images with 1,000 categories. So this 1,000 categories is very interesting. So uh, when you start running it and when you start looking at labels, training model labels I'm looking at over here, I'll have to understand this further as to, what exactly is this. So what image label is 6, what is 7, all of this I need to understand. But I got about 1,000 printouts here in the log file that I was trying to create, just for one epoch. So yeah, that's for the labels. I'll come back to that. Or a fixed feature extractor for the task of interest. The three major transfer learning scenarios look as follows. So there are three scenarios which are given. The first one is a convolution network as fixed feature extractor. So you're basically doing a triple F, a fixed, sorry, FFE, a fixed feature extraction. So take a convolution network pre-trained on ImageNet, remove the last fully connected layer. This layer's output are 1,000 classes scores for different tasks like image. So these 1,000 categories. So the last layer will obviously predict 1,000 different class scores for different tasks like ImageNet. Then treat the rest of the convolution network as a fixed feature extractor for the new dataset. So you have a new dataset, you are not wanting to predict 1,000 classes of ImageNet, and maybe your dataset is just printing maybe 10 classes like cipher 10 or cipher 100, or mnest or something which is there. So a much more smaller number of classes. For like mnest digits, I think if I remember correctly, you'll have 10 classes only. Or like what I might want to do, I want to do airplanes and no airplanes, right? I did that last time also with one simple net, and now I want to do it with this. So there I'll just have two classes, one positive for airplanes, one negative for airplanes, right? So then in an AlexNet, this would compute a 4096 vector for every image that contains the activations of the hidden layer immediately before the classifier. So the classifier is the last layer, but the activations of the hidden layer immediately before that layer. So we call these features CNN codes. So I don't necessarily understand this 4096D vector. Oh, maybe this is like the image 2 vector vector which will come out of AlexNet, is what I presume. In another network, I think it was 2048 or something. Yeah, in AlexNet, maybe it is 4096. Okay, maybe that is what it is. So it is important for performance that these codes are ReLU'd, okay, thresholded at 0, if they were also thresholded during the training of the convnet on ImageNet, as is usually the case. So it is important for performance that these codes are ReLU'd. So you want to basically have either a 0 or a 1. That is what they mean by ReLU'd. They were also thresholded during the training of the convnet on ImageNet. Okay, so if it was done while training it on ImageNet, you want to do it again now when you're using it for your own fixed feature extract, using it as a fixed feature extractor. Yeah. Okay. So that is one thing. The second thing is fine tuning the convnet. So this is more involved. Fine tuning the convnet. Mm, wait, I have one more link that I need to look up, but I don't want to open this file. One second, just give me a second. Okay, so there is few other things that I noted. I don't remember the source. I'm not able to quote that right now, but still, So the setting requires grad, which is requires gradient, should be the main way you control which parts of the model are part of the gradient computation. So for certain parts of the model, the gradients will be computed where the setting would be requires grad. So if the setting is requires grad, okay. Uh, so control which parts of the model, fine. For example, if you need to freeze parts of your pre-trained model during model fine tuning, so you will use requires grad false, right? You want to freeze parts. You want to either freeze parts or you want to lock that down, right? To freeze parts of your model, simply apply requires grad false. Okay, so this requires grad, it will have to be false to the parameters that you don't want updated. So certain parameters, as in certain weights of the initial layers, you don't want them to be updated. Okay, and coming back here, the second strategy is, and this is basically the second strategy. So I don't remember where I copied this from. I copied it from somewhere. Then the second strategy is to not only replace and retrain the classifier on top of the convolution network on the new dataset, but to also fine tune the weights of the pre-trained network by continuing the backpropagation. So you want to fine tune the weights of the pre-trained network by continuing the backpropagation. So this is not what we are doing here. So if you say requires grad false, then you are not doing that, right? Then you're doing the opposite. Fine. Then you are freezing parts of your model. Here we are not freezing parts of the model. It is possible to fine tune all the layers of the convolution network, or it's possible to keep some of the earlier layers fixed. So when we say keep some of the earlier layers fixed due to overfitting concerns and only fine tune some higher level portion of the network. So I'll stop here. So this is what is recommended over here also, right? So uh, keep some of the earlier layers. Earlier layers means the layers which are closer to the input layer. The layers which are closer to the input layer, the layers which will be getting us non-specific features or generic features. Those will be the earlier layers over here, and the later layers or the deeper layers would be the layers which come closer to the output layer. So anything which is further towards the right, so to say, or closer to the output layer will be the deeper layers or the not earlier layers or the later layers, so to say. So then this is motivated by the observation that the earlier features of the convolution network contain more generic features, edge detectors or color blob detectors that should be useful to many tasks, but later layers of the convolution network become progressively more specific to the details of the classes contained in the original dataset. So yeah, when it says original dataset, so what it basically means is that if say for ImageNet or say for any other dataset that you have trained it on earlier, and from there you have extracted this convolution network layers, then the later layers or the deeper layers will be more specific to that particular task or more specific to that particular dataset, right? So like he says, okay, yeah. So in case of ImageNet, for example, which contains many dog breeds, a significant portion of the representational power of the convolution may be devoted to features that are specific to differentiating between dog breeds. So now if you are doing some kind of object detection or some kind of image recognition or whatever it is that you're doing, which does not involve dogs, then you probably don't want what is happening in the later layers. You are not really concerned about that. Yeah. So this is one thing. Then they talk about pre-trained models. In model convolution networks take 2-3 weeks to train across multiple GPUs on ImageNet. It is so why? Because ImageNet is a very large network with 1,000 classes. So yeah, that's why it will take so much time. Common to see people release their final convolution network checkpoints for the benefit of others who can use the network fine tuning. For example, the cafe library model zoo. Okay, fine. Fine. So yeah, this is one. So going back to the code, and yeah, so this is what I actually ran my first initial this thing when I ran it, test underscore one.py, the same code for the first time when I ran it. This is what I got. So the Cipher dataset got downloaded. Yeah, and I got this directory created over here. Right. So I've not really gone into the details of what this is and how this is and what is happening here. Uh, but I am presuming these batches of data got extracted, and these are obviously these are binary files. Can't. So we'll have to Google it later on and see as to what exactly is happening. Let me just put it in the git ignore for now. Okay, going back to my yeah. So and then when I run it again, so obviously it says files already downloaded and verified. So it's not downloading those files again, which is great. Uh, Going back to the code. Okay, so this is how we can end up understanding the. We did not understand the normalized part of it. We jumped here. Mm, where did I open that? Yeah. So this is quite detailed, and again, I wanted to look at one particular. Yeah, transform methods above all transform data into normalize range -1 and +1. If data set is already in range 0, 1 and normalized, you can choose to skip the normalization and transformation. You can choose to normalize and get data in. So there are various methods which are mentioned all over this place. And also, so this is pytorch.org, and this one is discuss PyTorch. And there's another one which was there. Uh, this is again beyond me for now. This is, I don't know, I think I lost that link. No, this is the one, yeah. So this is on the Fast AI forums, and again, very interesting explanations. Mm, Especially this one, and there is one more which is there, which I ended up copying down here. I wanted to kind of play with this later on. So the sources, yeah, again, this is response number 9, I think. Nah, this is the one. So David Lopez, he's given this bit of code, which will if you run this, it will help you understand as to how the mean and the standard deviation is being calculated over the entire data set. So Cipher 10, Cipher 100, and I think MNIST. Yeah. So these three he's given. I have taken that. I've just put it over here, down here. I want to play with it later on and understand as to how this can be done and how it is beneficial, or why I would want to do it. So it will basically help me understand what will be the mean and standard deviation for any data set that I am using. So right now over here, this is most probably for ImageNet is what I'm presuming. And so, okay. So this is the train data transform, and we looked into a little bit of what transform, normalize, and all of this is. Okay, then we are creating a train set. So we are taking that data set. So Cipher that's just got downloaded. A train true, download true. So download true is okay for the first time. Second time it will on bounce off. It will not download. Then and what is the transform? The transform that we've just written up here. So this is the transform that you're passing in. So this is what the train set. Then you from this only, then you get a train loader. From the train set you get a train loader, and that you get through the data loader. So this data loader I've seen a couple of times earlier. This is also defined in certain other code and other references that I've done earlier. It is defined as a custom data loader, also as a custom class. So that is also okay, where the num workers and other things you can specify. Over here that is not done, which is fine. So that is okay. There you go and specify the init and the, there's one more, right? So there's init and yeah. So all of this I've gone through earlier. Over here, they're not doing a custom data loader, which is fine. So I'll just skip over this for now. Then comes the validation data transform. So again, this transform is similar to what is happening over there for the training, and similar is happening for the validation, but these two are not there. So there is no horizontal flip or vertical flip. So that's not there. Okay. Then you create a validation data set out of that from the same cipher. Then data loader validation uh, order from that. Okay, similar to what was done above. Then you specify your device CUDA, or okay, so for when I ran this, this was my GPU status when I ran it some time back. So initially it was at 64%, 95%. Then again after some time 65, 94, and if I'm not wrong, that is what, 1 GB 345 MB. Yeah, and total capacity of my GPU is around, I think, 4 GB. And so volatile GPU utility, that's at 94%, and the temperature and the fan utilization and all that. Yeah. So now if I run it, so it's already gone through one epoch and it's not training anymore. So now we see this is all at 0, 48%, whatever. So yeah, okay. So we are defining the train model method over here, and I wanted to see how many times this method gets called in one particular epoch, and that is what I got to see over here. So if I say in here train model, so okay, this enters once, and after that, I'm this I got 1,000 times, right? So this particular enumerate has ran 1,000 times. Why it has ran 1,000 times, I'm not sure, because 512 is the input size that I got. I got that somewhere in the code, and I wrote it down here. 512. Yeah. So when I print this model FC in features, so what is the count of the num features? That is 512, and for some reason I'm getting this as printed as 1,000 times. This labels that I'm printing. Okay. But okay, I'll try and understand what this is. So send the input labels to the GPU. So input and GPU labels have gone to GPU, to device. Then optimizer zero grad. We don't want the gradients from the earlier runs. So over here you will zero the parameter gradients, right? So this is the comment from the book only. So you will make the parameter gradients zero from the earlier runs. Then one second. Yeah, so I earlier googled this. I got this from Stack Overflow, and so what exactly is model eval and what is zero grad? So model eval. So over here, what we see, this is model trained, and down below here is model evaluation, right? So it says model evaluation has effect only on, and this is a comment. This is actually a comment at this Stack Overflow question. It says model evaluation has effect only on layers, not on gradients. By default, gradient computation is switched on, but using context manager torch no grad, right? So whether it is zero grad or no grad, so here you are making the gradients zero at that point of the optimizer when that is running, and here during evaluation allows you to easily turn off and then automatically turn on gradient computation. Okay, that is one. The second thing is So model evaluation, when is a model in evaluation phase? That it is in inference or you're testing, right? So over here, like we are calling it testing, test model. Yeah. And this is from this particular question. So it says model eval is a kind of switch for some specific layers, parts of the model that behave differently during training and inference, which is evaluation time. For example, dropout layers and batch norm layers, etc. You need to turn off them during turn off these layers during model evaluation, and eval will do it for you, right? So because you've put the model in eval mode, these layers will get turned off. Okay. Uh, these layers are only required during training time, are not required during evaluation time. In addition, the common practice for evaluation validation is using torch no grad, right? In pair with model eval to turn off. So you will have model eval also, and you'll have torch no grad also. And similarly over here, we have got torch zero grad. Sorry, optimizer zero grad. But do we have it in test? No, we only have it in train. I don't think so. You have it in test, optimizer zero grad. Okay. So that is what it is. And then with torch dot set grad enable true, you're getting outputs by providing that model inputs, right? The inputs that we got here, up here, we got this from data loader. And then torch max outputs, we're getting predictions, and we're getting one more value. That other value we are not using. So we're getting a tuple out and getting to use only predictions. Then the loss function, outputs and labels, and the loss is getting backward propagated, and then optimizer is stepping through to the next step. Then the current loss is calculated and current accuracy is calculated, which are both initialized as 0 up here. Once this is done, then total loss and total accuracy, and then you print that at the end of the training for that epoch. Okay. When I ran this, what I got was this at the end of it: test loss and accuracy. Did I get train loss also somewhere? I'm not sure. I'll have to check. I did not check earlier. Yeah. So train loss is this, and accuracy is this. And this is just when it ran for one epoch. Okay. Yeah. So this is what the situation is now. Let me run it again for more than one epoch, and then I'll get back to this.